Depth first search and breadth first search, or DFS and BFS, are graph algorithms for visiting every single node within a graph. This might be used, for example, when we are searching for a particular value within a graph. In this case, we probably wouldn't need to search through the whole graph, but we can if we want to. DFS and BFS work with most types of graphs, but today with these examples we're going to see binary trees because it's a bit easier to see the process of what's going on. I've made it so that we have to enter a name for every single node. This makes it easier to tell the nodes apart when we start searching through. So let's just name this A, B, C, D, E, F, and G. Now, with a generic graph, with depth first search and breadth first search, you'll usually have to specify a starting point. With a tree, however, we typically use the root of the tree as our starting point. Before we go any further, I want to quickly mention recursion. So recursion is a definition that uses itself. It's a bit of a tricky concept to kind of work with, but an example might be your ancestor is your parent or your parent's ancestor. So, for example, we know that our grandparents are our ancestors. Using this definition, our recursive definition, we can say, okay, well, our parents are our ancestors, and from the point of view of our parents, their parents are therefore their ancestors, and because our grandparents are our parents' ancestors, they are therefore our ancestors as well, because our ancestors are our parents or our parents' ancestors. It's a very strange concept to start to work with, but another way you could think about it, perhaps a more common application, is when writing a program, if you define a function and inside of that function you have a call to that very same function, that is recursion, and it's a concept that we make use of in breadth first search and depth first search. So from our starting point at A, we have two choices. We can go down to B or we can go down to C. And so how do we choose which one to traverse? Well, B versus C doesn't really matter, but what we're going to do is we're going to add both of them to a stack, which is last in, first out, or first in, last out. So if we add them both to a stack, let's say we have C at the bottom and then B on the top. The next node that we are to traverse is going to be this one at the top of the stack, which is B. So when we traverse B, and let's put this in, so we've got our A, which is our starting point, and my webcam is slightly in the way again, so I'm going to move it back down to here, and you can still see the G. So we start with A, we add both of the children to a stack, so C and then B, and then we pop B off of the top, and we add B's children to the stack. So we add an E and a D on top. We still haven't traversed C, which is down here. We're going to come back to that. So the next item is going to be D, which is the leftmost child of a given node is always going to be the first one or the next one to be traversed. So if we go to next, we've got D. Now, D doesn't have any children, so we're not going to add anything else to the stack. And what this means is the next one underneath can now be traversed instead. So what we do is we go back to B and we say, okay, B, you've already traversed your left child do you have any other children that need to be traversed? And B does. B has E. And that's represented on our stack. Currently we've got our C down here and our E just on top. So we pop E off of the stack, and that's what we traverse next. And now E doesn't have any children, so we go back up to B and back up to A, and our stack currently just has a C on it. So that's the next node to be traversed. We go down to C and we repeat the process. So we go to F and we go to G. So we got A, B, D, E, C, F, G. So we can also see visually that we are going as deep as we possibly can. That's why it's called depth first search. We're going as deep as we possibly can. So we're going to B, and then we're looking at B's children before we finish traversing all of A's children. Like this. Explaining how depth first search works with a stack was perhaps a little overcomplicated, but I did it for a reason. Because when we look at breadth first search instead of depth first search, we have the same starting point. We start with A, and we have the options B and C. But this time, instead of adding the options, instead of adding the children to a stack, we're going to add them to a queue. And what this means is the next node to be visited after A is going to be B, and then the very next one after that is going to be the other child of A, so C. We're going to have B and then C. So we traverse B, and we add B's children to the stack, so D and E. But this time, D and E are going to be after the C. So you're going to see the next one is going to be C. We add C's children, F and G, to the queue. But again, they're going to be after D and E. And so with a stack, we're trying to go as deep as possible, and then come back until we have another option to go deep. And then we go right up to the top and we go to the other side. With breadth first search, we've got kind of like a level by level kind of idea going on. We're going as broad as we can. We're traversing as many of the children, or all of the children, and then we're traversing all of the children's children. And that's all there is to depth first search and breadth first search. In the next and final video, we're going to be looking over some of the data structures and algorithms that we've already seen with big O notation.